Hello everyone. In this session, we are discussing with respect to the basic structural integrity and as well as the adaptability. A study of the natural materials, structures such as the tendon, bone, wood, and the shells is reveals that the living organism builds the material and develops its architectural starting from a level well below that of the living cell. The tendon, for example, is which serves a link between the muscle and as well as a bone, has extremely intricate complex structure with a six discrete level of hierarchical organization. The triple helix tropocollagen arrangement at the lower end, the scales makes up the microfibrils approximately estranged and surrounded by a tetragonal lattice of subfibrils. These in turn are packed and enveloped by an additional fibrous structure which is as shown in the figure. This multi-level structural arrangement results in a tough structure with a non-linear and a reversible properties. See, this is a schematic diagram of the tendon which has been linked between the muscle and as well as the bone. This it consists of totally six different structures. These structural uh, view it has been evolved in the ACM, which is nothing but the scanning electron microscope. The tendon fascicle fibrils. These are the first three portion which is having a interconnection between the between connection to the bone, and the subfibrils, microfibrils, and tropocollagen are the other three which is having a structural fibrous structure. These having a integrity for the bone. The rope-like structures which mimics to some degree of a tendon architecture is also as discussed in the further slides, and ancient man-made structural components that have withstood the test of the time, mining, marine, and as well as the elevator industries. If you take an example of the ropes are the metallic ropes. In the metallic ropes, where the n number of wires are twisted, even these wires, what it has been twisted, is of the smaller diameter. Another example is nothing but the normal rope what we seen, which is fabricated by means of the coir. The coir fibers what they use is for the formation of the rope, where the coils are twisted at an angle. These by twisting and clubbing with a number of coir fibers, what the strength of the what we can say the rope is also increasing it. See, this is the what we can say the mechanism or the structural behavior where the integrity and as well as uh, the concept which has been implemented in the nature is implemented in the man-made structures, like either it may be a guy wire or it may be a rope. The numerical results from a parametric study of a single strand in tension indicates an increase in toughness with a increase in ductility of the element. The parameters in the figure is a ratio of the areas of the inner and as well as the outer fibrils. See here the rope concept, or it may be the rope architecture, it has been explained. Here in the case of the rope architecture, where the n number of micro, or it may be a very small wires are clubbed together to form a rope. Even these also it is inclined, and where the ductility or the strength and as well as the toughness matters. There are two important consequences or subdivisions of the hierarchy of the elements are discussed above. The first thing is there is a loss of stiffness at the higher hierarchical level. This reduction can be as substantial. For examples, in the case of the cellulose, the Young's modulus of the crystallitis has been estimated around 250 GPa, but the experimental value in the well aligned parallel the systems and the microfabrics is only of order 70 GPa. The second consequences of the hierarchical arrangement appears to be a compensated for the loss of the stiffness discussed above by the increasing in toughness. Such deformations occurring at a very large number of interfaces contributes a energy absorption leading into a better structural integrity. This concept has been implemented even in the fabrication of the rope or even in the fabrication of the metallic guy wires. Thus, in the natural systems, a judicious combination of elements, materials, and as well as the components of the different strength in the same structure leads to an acceptable and adequate hybrid system whose property are tailored for a specific usage. The variety of such designs is made possible by the hierarchical interaction between the material and the structure. Even in this, the best example is nothing but the climbers. The climbers which will withstand a very huge, either it may be vegetables or it may be a fruits. This integration approach seems to be one of the design rule and the key strategy with which the nature achieves that exclusive but aviable objective of balancing the strength and the stiffness without sacrificing the toughness. The adaptability. The second concept where the nature has implemented is nothing but the adaptability. A good example for the adaptability of the living organism to adapt the change in loading condition is nothing but the bone. The living bone continuously undergoes a process by which it remodels to accommodate the change in its loading. The time scale of the process may be of the order of the month, but it can begins within a minute of an impetus. Cyclic strain hysteresis are found to be a more effective than a steady strain hysteresis including a higher remodeling rates. The best example for the adaptability is said as the bone. See, if you start discussing with respect to the bone, and if you start comparison between a man who is carrying a gunny bag with a load of 100 kgs and a normal man who is carrying a load of 5 to 10 kgs, where the bone it remains same even in both of us are the same material, but the strength parameters or it may be the toughness parameters what it has been remarkably implemented in a person who is carrying a load of 100 kg is a totally different with respect to the a general human being. See, this is a one best example for the adaptability and as well as the marvelous principles which has been implemented in the loading condition of the bone. The another example with respect to the bone is a person who with a weightlifter who is lifting a 100 or it may be a 500 kg, but and also the same normal common man where he can lift a maximum of 50 kg. The bone remains same in the person with respect to the weightlifter and also the normal man is of same, but the what we can say the structural design in the microstructure of the bone is totally different, and even that is also uh, it cannot be obtained, or that those type of what we can say the behavioral or it may be the growth, it cannot be obtained within a minute, but it can be obtained by for a period of a month or together. This is a structural explanation with respect to the stresses and also the what we can say the strains and also the principal axis. Even it varies with respect to the directional loading also.